Right, so can you see the first question on the screen? I'll start the solution.
Yes, sir.
All right. Okay. So the first question is we have two dice and we are uh, rolling them independently. So what is the expected number of so essentially what is the sum of the numbers uh, that we'll see on the dice in expectation? So so let's say uh, there is n1 is a number that shows up on the first dice and n2 on the second dice. N1, n2 are both uh, numbers from 1 to 6. Uh, then what is the expectation of n1 plus n2? So the expectation of n1 plus n2 is equal to the expectation of n1 plus expectation of n2. This is from the linearity of expectation. Uh, N1 and N2 are both thrown independently. So they have the same um, expectation because they are identically distributed. So that makes it equal to 2 times expectation of N1. Now expectation of N1 is equal to 2 times probability P of N1. N1 equals I times I, where I is from 1 to 6. So this comes out to be equal to 2 times 1 by 6 times the sum of the first 6 um, integers, that is 6 times 7 by 2. And so the answer is equal to 7. So 7 is the correct answer. Okay. So 7 is the correct answer. I hope it's clear, right?
Yes, sir.
All right. Um, we move on to the second problem.
Yes, sir.
So in general, how are you feeling about the course? The course I assume is in week 3, right?
Yes, sir. It is week 3 going on.
All right. So in the second problem, there is a die that is being thrown, but the die has 2021 sides. Um, and so the probability that face K appears is directly proportional to K. So essentially, we have a random variable, a discrete random variable. Uh, let's call it X. Uh, and X takes values from uh, 1 to N, where N equals 2021. And the probability of X being equal to some K is equal to alpha times K. Alpha is a fixed constant. So what is the expectation of of x is the question. So first of all, this constant alpha has to be determined. So in particular, we know that the sum of the probabilities should add up to one. So probability sum over of probability x equals k should add up to one, which means that sum over of alpha times k equals one, which means that alpha times n into n plus one by two equals one. Now we have to find out the expectation of x. So expectation of x equals sum over of k times probability of x equals k. So that is equal to sum over of k. K is from 1 to n. K times alpha k. So that is equal to alpha k squared. So that's equal to alpha times sum over the sum over of k squared, k from 1 to n. So that's, we know, the sum of the first n natural numbers squared, that equals n into n plus 1 times 2n plus 1 upon 6. Now we know that alpha times n into n plus 1 by 2 equals 1. So this means this is equal to 2n plus 1 by 3. So uh, when you substitute n equals 2021, the answer is 1347.67. Just verify that. Yeah, you can stop me if in some place or something, if you want me to repeat or explain, uh, feel free to stop me.
Okay, okay, sir. So in this question, everything is I've got understood the solution.
Hmm. Okay, so will I move on to the next problem?
Yes, sir.
All right, great. There are in particular two problems which I found to be um, slightly not so easy. So okay, so I'll let you know when we come to those problems. So this is a problem where we have a random variable x that takes values 1 or 2 with equal probability, and y is a random variable that takes values between 1 and x plus 1 with equal probability. So this is a yeah, I mean, the way you this question is not so nicely framed. Um, So y is a random variable that takes values between 1 and x plus 1 with equal probability. So okay, but anyway, so essentially the way I think we have to read this problem is we have to assume that there is a conditional probability being, so there's a conditional probability being given to us. So the distribution of x is obviously clear. X takes values 1 or 2 with equal probability. uh, the distribution of y is expressed in terms of two conditional distributions. So, so there are two conditional distributions. One is x, sorry. One is y given x equals 1. And there's another which is y given x equals 2. Okay. Now the first conditional distribution says that um, um, so let's call them as two random variables. Let's call it as y1. So y1 is y given x equals 1, and y2 is y given x equals 2. So y1 takes values from 1 to 3, because when x equals 1, sorry, when x equals 1, y1 can take values 1 and 2. Uh, so y1 can take values 1 and 2, and y2 can take values when x equals 2 equal, it can take values 1, 2, and 3. Again with equal probability. So from this we can figure out the distribution of y. So the probability of y being equal to some r, where r is 1, 2, and 3, equals probability of y equals r when x1 equals 1 times probability of x equals 1 plus probability of y equals r given x equals 2 times probability of x equals 2. So that is just equal to probability of y1. Probability of x equals 1 is half, uh, plus probability of y2. Uh, Again, probability of x equals 2 being half. Um, right, so there's, sorry, probability of y1 equals r. So y2 equals r. Okay. Um, so this is how we can compute the probability of y. So the distribution of y gets computed in this way. Now we have to compute expectation of x plus y. So expectation of x plus y equals expectation of x plus expectation of y. Expectation of x you can easily compute. Expectation of y you can easily compute. Uh, so I'm not doing the explicit calculation. You can just figure out the computation yourself. It's just need to substitute the values, and it comes out to be equal to 13/4. Okay. So if this is clear, uh, I'll state the last two problems, which are somewhat interesting, more interesting than these. Okay, okay. So this question is Alice flips a coin n times. Okay, and Bob flips a coin n plus 1 times. Both are fair points, so head and tail appear with probability half, respectively. And so we have two random variables x and y. So whenever uh, whenever we toss a coin, um, there is an associated binomial random variable which counts the number of heads or the number of tails. Uh, so in this case, let's assume that x is a binomial random variable um, that computes the number of heads. Similarly, y computes the number of heads that Bob gets when he flips the coin n plus one times. Um, so let's just write it. So x is a binomial random variable with parameters n and half. Y is also a binomial random variable with parameters n plus 1 and half. Okay. So um, so we are required to compute the probability. What is p? Uh, p less than px less than 1. In other words, what is the probability that Alice sees fewer heads than Bob sees when he's tossing the coin? So before I describe the solution, have you solved this question? Do you know the answer, or would you like to uh, attempt to answer this question?
No, sir. Let's. Uh,
Okay. Uh, so so uh, so there hasn't been a question of this kind in this week's assignment for the course, is it?
yes, sir. There is assignment, and
And you have a question of this kind, is it? Do you have a question of this kind where
yes,
is a
sir.
coin
Yes, sir.
being tossed? Oh,
Yes, sir.
okay,
I have a
okay,
point.
okay.
I
So
have
did
the.
were you able to attempt that question?
So actually, I haven't tried this question yet. That's why.
Okay, okay, okay. So any idea how you try to attack a question like this? Um,
X is less than Y. Sir, this question is asking like,
yeah.
what is the probability that Alice get less heads than Bob gets when?
Yes, exactly. Yeah. So we can rephrase it in this way. Uh, Probability that Alice gets fewer heads than Bob. Yeah. So this is what the question asks us to do. Yeah, you're right.
Yes.
Yeah. So there is a hint given in this question. Um, so I did a solution of this question without making use of this hint. Um, perhaps perhaps there is a way to make use of this hint. But anyway, so if you see a question of this kind, uh, in general, let's say if you see a question of this kind where you have two random variables, um, So let me just write it. So sometimes I'll not directly solve the question, but I'll also give like hints to solve a more general version of this problem. So let's say more general question. So let me just write this more general question. So if Z1 and Z2 are discrete uh, random variables, um, they may or may not be identically distributed, but assume that they are independent. Independent. So assume that Z1 takes uh, values, some values, let's say it takes some values, let's say from 1 to R1, and Z2 takes values from, let's say, 1 to R2. Okay. So if we ask the question, what is the probability that Z1 is smaller than Z2? So, so Z1 and Z2 are two independent random variables. So the values that they can take are they take it independently of each other. So, so so if you consider this set, which is okay, so consider this set. We consider this set 1 to up to R1 cross 1 to up to R2. So this is basically pairs. We have pairs of numbers A1, A2.
Yes, sir.
It's basically pairs of these kinds. And A1 is the value that Z1 has taken, and A2 is the value that Z2 has taken. So, so when we ask probability of Z1 and Z2, we essentially have to compute all those, or you need to enumerate all those pairs A1, A2, where, so let me write it out. We need to enumerate A1, A2, all those pairs A1, A2, where A1 is less than A2. Okay, but it's not enough to just find out the pairs. We also need to compute the probability associated to seeing such a uh, uh, such an occurrence. So the probability that Z1 takes A1 and Z2 takes A2, because Z1 and Z2 are independent by assumption. So that is equal to probability of Z1 equals A1 and probability times probability Z2 equals A2.
Me too.
So let's, for simplicity, let's write it as F1 of A times F1 of A1 times F2 of A2, where F1 of A1 is probability Z1 equals A1. Okay. So now the probability of Z1 less than Z2 equals sum over A1, A2, all those pairs A1, A2, where A1 is smaller than A2, F1, A1 times F2, A2. So this is the probability of Z1 being smaller than Z2. Is it clear how we can compute in general?
Yes, sir.
Okay. So now let's try to use this for the current problem. So for the current problem, we have two random variables, X and Y. So these are not only independent, they are independent, but they're not identically distributed. So they're independent, but not identically distributed. So can you tell me why they're independent?
Because uh, Alice is tossing one coin and Bob is tossing another coin, so both of them are independent events. So that's
Yes,
why
yes. Yeah, you're right. But why are they not identically distributed?
because one has n chances and another has n plus one chances.
Yeah, exactly, exactly. So X is uh, binomial random variable in parameters n and half. Y is a binomial random variable in parameters n plus one and half. So they're
And
not
yeah,
identically distributed. Okay. So what are the values X can take? So X can take values from 0 to n, right? And
yes, sir.
Y can take values from 0 to n plus 1.
Yes, sir.
Okay. So we need to compute all such tuples. So we need to consider the set 0 to n cross 0 to n plus 1. So essentially we'll have to look at all tuples r comma s, where r is smaller than s, and the probability of, so r comma s means that uh, Alice has r heads and Bob has s heads. But for x to be less than y, we need to enumerate all those tuples r comma s where r is smaller than s. So first we need to, so first by this formula, the probability of x being less than y equals probability sum over of uh, probability of x equals r, y equals s over r comma s, where r is smaller than s, right? Um, okay. Now, what is probability of x equals r, y equals s? So they're independent. So that is equal to uh, sum over of r comma s, r less than s, probability x equals r, probability y equals
Y
s.
equals X.
Yeah. So these are binomial random variables. So we know that the probability of x equals r is equal to,
NCR up into half to the power n.
right, exactly. So if NCR times 1 by 2 power n, and this is equals n plus
N
1
plus
CR
CR,
half
so
to the power.
CS it will be
Huh?
S N1 plus 1, N
Ah, yeah,
plus
yeah,
1
yeah. Sorry.
S,
Yes, yes, exactly. Yeah, yeah, absolutely.
and
Times
to the power n plus 1.
1. Yes, right. So this comes out to be equal to 1 plus 2 to the power 2n plus 1 times r s, r less than s, ncr times n plus 1 cs. Okay. Now, this is not an easy computation, obviously. Um, so you have these binomial coefficients, and you need to take the product of the binomial coefficients. Now, this is not a trivial thing to compute. So essentially, to elaborate this a little bit more, what we need to do is we need to do this. We need to do 1 by 2 to the power n plus 1. I'm just rewriting this sum only, nothing else. Sum over of s equals 1 to n plus 1. Sum over of r equals 0 to s minus 1 ncr, then times n plus 1 CS. Is it clear? I'm just rewriting this formula in a more uh, so I'm essentially collecting the terms. So I'm considering an S, um, and then I'm considering all those R's which are smaller than S. So for a fixed value of S, I'm going to consider from R equals 0 to S minus 1, and this is what we get. Now, this is like we can compute. So let me write it down. We can explicitly uh, compute this sum, but it's not trivial. I mean, there exists analytical expressions uh, where we have the sum of the first k binomial coefficients, and we can where we have the sum of the first k binomial coefficients, and we can say what is the sum of that. But that's not very easy. It will lead to some uh, involved calculations. So the question is there a way to answer this problem uh, without doing explicit computation? So let me write it down. Um, can we bypass the explicit computation involving sum of products of binomial coefficients? Okay, so somehow we need to bypass it because otherwise we'll have a tough task on our hands. So to do this, we're going to make some observations first. Okay, a few observations. Okay, say uh, so let's call them one. Number one, say Z1 and Z2 are IID random variables. Then assume that they're discrete. Yeah, assume that they're discrete. Z1 and Z2 both discrete. So the first observation is that probability of Z1 being smaller than Z2 is equal to the probability of Z2 being smaller than Z1. Can you see this?
Probability of Z1.
Hello, I can't hear you.
Actually, sir, I was trying to visualize this thing.
Yeah. So right. So let's say you have two random variables. Uh, let's say you are tossing a coin n number of times, and you have
Yes,
uh, uh, let's say you and I are both tossing a coin n number of times. Uh, I count my heads, you count your heads. So let's say Z1 counts your heads, Z2 counts my heads. Then the probability that you get more heads than me, Z1 or yeah, then the probability that I get more heads than you is actually the probability that you get more heads than me. So there's a symmetry. So you can argue this from symmetry. So Z1 and Z2 are identical and so they're independent and identically distributed. So argue from symmetry. Uh, that probability of Z1 being smaller than Z2 equals the probability of Z2 being smaller than Z1. We can also explicitly argue this. So if you're not convinced by this symmetry argument, we can explicitly do this. So let's say they're discrete random variables. So if they're discrete random variables, then probability of Z1 being smaller than Z2 equals sum over of uh, all those pairs R comma S, uh, probability of uh, Z1. So R is smaller than S. Z1 equals R. Probability of Z2 equals S. Okay. Now, right. So what you can do is uh, you can flip them. So you can write this as equal to sum over of probability of Z1 equals S times probability of Z2 equals R. So why can you flip them? Well, you can flip them because probability of Z1 equals S is equal to probability of Z2 equals S, right? Why? Z1 and Z2 are identically distributed. So because Z1 and Z2 are identically distributed, probability of Z2 equals S is equal to probability of Z1 equals S, right? Similarly, probability of Z1 equals R is equal to probability of Z2 equals R because they're identically distributed. So you can write this in this way. So if you write it in this way, so then what is the sum over? The sum is over all those pairs R comma S where S is bigger than R, right? Because here we took the sum over all those pairs R comma S where R is smaller than S. Is this we are taking the sum over the same pairs R comma S, but here R is less than S, means that S is greater than R, obviously. So what this sum is equal to is it's the probability that Z1 is bigger than Z2. So so let's say you are asked to compute probability Z1 bigger than Z2, then what would you do? You take a sum over all those pairs S comma R where S is bigger than R. This is exactly what you do, right? And this is exactly equal to this sum. So probability of Z1 being Z1 less than Z2 is equal to probability of Z1 greater than Z2. I hope you can now explicitly see this, right?
Yes, sir.
Okay. So you're going to make use of this argument somewhere. Now, the second argument is uh, okay. So let's see how to use this argument. So notice that you have three events. So if Z1 and Z2 um, uh, are IID random variables, um, so Z1, Z2 are IID random variables. Okay. Then there are three events possible, right? So the first event is Z1 is smaller than Z2. This is one event. Another event is Z2 is smaller than Z1. And another event is Z1 equals Z2. So there
Yes,
are
sir.
three events possible. And these three events are obviously mutually exclusive. So if Z2 so the intersection of these are so if Z1 equals Z2, then obviously these would be false. And if this is true, then the rest would be false. This is obvious. So they're mutually exclusive events. So they are mutually exclusive events. Okay. So what does this mean? So it means in particular that if I sum them up in probability, they're equal to 1. So probability of uh, Z1 smaller than Z2 plus probability of Z2 smaller than Z1 plus probability of Z1 equals Z2. This must be equal to 1. Okay. But probability of Z1 smaller than Z2 and probability of Z2 smaller than Z1 are actually same, right? They're equal. We computed it, right? So
Yeah.
it turns out that probability of Z1 equals Z2 is equal to 1 minus um, or I mean just okay. So it just means that probability of Z1 smaller than Z2 is equal to 1 minus probability of Z1 equals Z2 upon 2 because these two are equal. So this is clear, right?
Yes, sir.
We have this expression with us. Now, how are you going to use it in this problem? Uh, we do not want to do this hefty calculation. We want to bypass it. So, so let's look at the data that we have in the problem. So Alice is throwing the dice n times. Bob is throwing it for n plus 1 times. Right. So Bob's count is maintained by this random variable y. A's count is maintained by this random variable x. So
Yes.
so let's declare one more random variable. Let's call it y prime. Okay, so y prime counts Bob's uh, heads in the first n throws. So Bob throws for n plus 1 times. So there's a random variable y prime that I define, which is basically Bob's count in the first n throws. Okay, and I declare one more random variable. Let's call it I. So I is basically Bob's count in the last throw. So I is equal to 1 if Bob gets head um, in n plus 1 in n plus 1th turn and 0 if otherwise. So I'm essentially splitting those n plus 1 throws into the first n throws and the last throw, right? So I can write y as equal to y prime plus I, right?
Yes,
Y
sir.
prime is my count in the first n throws, I is the last throw, basically. So now notice that x and y prime are IID.
Yes, sir.
Is it clear? They're both binomial. So they both count n throws, and they're of course independent and identically distributed. So x and y prime are IID random variables. Now the probability. Notice what does x less than y mean? So x less than y means two events are possible. One is x is smaller than y prime, right? If x is smaller than y prime, obviously x is smaller than y. Alternatively, it's possible that x is equal to y prime, but
And
I
I is equals
equals
to
1.
1.
So it's clear? It's clear, right? Ha. Okay, great. So, but notice that I, y prime, and x are all independent of each other. I is the last throw. It's independent of what has happened in the first n throws and what Alice is getting. It's independent. So I, x, and y prime are all independent. So let me just write it. I, sorry, x, y prime, and I are all independent, are mutually independent. Okay. So in probability, what this means is that probability of x less than y equals, so these are disjoint events, obviously, uh, is equal to probability of x less than y prime plus probability of x equals y prime times probability of I equals 1. But probability of I equals 1 is equal to half, right? Because it's
Yes,
just
sir.
one throw, so probability of I equals 1 is just equal to half. Okay. Now, let's make use of this relation that we saw before, that if you have two IID random variables, in this case x and y prime are IID random variables, then probability of x less than y prime is given by this. So let's substitute this thing. So probability of x less than y prime. So let's call this relation as star. So from star, probability of x less than y prime is equal to 1 minus probability of x equals y prime upon half, plus this is equal to probability of x equals y prime by 2. And so if you add them up, you get half.
It gets rough. Okay.
So half is the correct answer. So nice problem, right?
Yes, sir.
So we have effectively bypassed the entire computation. Um, So we didn't have to compute sum of terms which had binomial expressions. Um, we just we just made use of the information in the problem. Okay.
Yes, sir.
Okay. So I see someone else has joined, but I think that person has left also. Okay.
So that means that some would also have been added up to half only.
Huh?
That the binomial sum of product would
Yeah,
also
yeah,
have been
obviously. Yeah. It would have
half.
added up to half, but that's the fun, right? It's we don't know. Yeah, I mean, so the thing which is very interesting, and it's true about probability, is that uh, you can get the answer to an expression of this kind. So let's say I give you a problem in combinatorics, okay, where I give you would have seen these problems, right, where we do sum of the first binomial coefficients, something like that. So let's say I give you the sum of the binomial coefficients of this kind, okay, and I ask you to compute the result. Okay, now it may be very hard to do it, but if you can find a problem in probability uh, such that uh, the answer to that problem in probability is equal to that binomial expression, but if you can argue, uh, and get the answer in a different way, then that gives you an alternative way to give you a solution to this thing, right? So
Yes, sir.
if this was the problem, I can make use of the result in this, and I can argue that this is equal to this. You get the point, right?
Yes, sir.
Yeah. So I mean, if you study higher combinatorics, higher enumerative combinatorics, so these kinds of probabilistic arguments are very powerful, where you bypass the actual problem, you find out an alternative problem. The solution of that problem corresponds to the solution of that problem, but that problem is a problem in probability for which you can argue in some different way, and that can give you the answer to the actual combinatorial problem. Yeah, these are very interesting ideas. The use of probabilistic techniques in combinatorics. So this is like a combinatorial technique in probability. So if we computed the sum of this explicitly and if that came out to be equal to half, that would be application of combinatorics in probability, but it can be the other way around also. We can use a probabilistic technique in combinatorics and argue it in the other way. Okay, so let's look at the final problem. The final problem was actually quite interesting, I thought. So notice that in this problem specifically, uh, we have not made use uh, of the hint that is given. So they have given a hint, right? This px less than y is something
Yes.
something, right? We have
Yes,
not
sir.
made use of this hint. Um, so I'm curious how we can get a solution by making use of that hint. Okay. Okay, so let's look at this problem. Can you see this?
Post office. Yes, sir.
Okay, post office problem.
Yes, sir.
Yeah. So what the problem is saying is a post office has two clerks. Alice enters the post office while two customers, Bob and Claire, are being served by the two clerks. She is next in line. Assume that the time a clerk spends serving a customer has the exponential distribution with lambda equals 5. What is the probability that Alice is the last of the three customers to be done being served? So did you understand the problem? So Alice enters the post office. So when she enters the post office, there are already two customers there, Bob and Claire. So let's quickly see how this looks like. So there are, let's say there are two customers. Um, so let's say there are like two counters, B is over here, C is over here, and Alice is waiting. So whoever leaves first, so let's say B left first, then A would join there. And if C left first, then A would join in that thing. Now the question is, what is the probability that Alice is the last of the three customers being served? So essentially what it means is, okay, so um, let's say B leaves first. B leaves before C. Okay. So then what happens is that A goes and joins, uh, B has left. So A has gone and joined that place. So A and C are now currently in the counter. But we are asking what is the probability that Alice is the last of the three customers to be done being served. So uh, it means that C, so the time taken to serve C, TC is greater than TB, but is smaller than TA. Is this clear?
Yes, sir.
So Alice, in this way, what happens? Alice is the last person to be served because the person C gets done before Alice, and Bob is of course done before.
And sir,
So
also TC less than TB less than
yeah,
TA
yeah,
also.
yeah. There is this other possibility also, right? Where you have TB less than TC less than TA. There's that possibility also. Exactly. So yeah, so there are essentially three random variables. One random variable for P, one for P, one for C. So the three random variables compute the time required. So notice that the three. So let's first define the random variables. X1 is the random variable to serve Bob. Uh, X2 is the random variable to serve Claire, and X3 is my random variable for for Alice. Okay. So x1, x2, x3 are all independent. I hope that's clear why. They're
Yes,
independent.
sir.
They're being independently served. And they're also identically distributed because both have exponential distribution. So x1, x2, x3 are IID random variables and sorry are IID and they both have the exponential distribution. Okay. Um, so just give me a second. I'll be back in like uh, 2 minutes. I'll just be back in 2 minutes. Okay.
Sure, sir.
Okay. Um, let's resume. Hopefully I'm audible. Okay. So yeah, so they are x1, x2, and x3 are IID, and they are both they have the both exponential distribution. So we are asked what is the probability that Alice is the last of the customers to be done so. Um, okay, so okay, so let's write this down explicitly. So we have two disjoint cases. Um, the first case, so let's write this event as E. So let E be the event. So let E be the event um, when Alice is the last customer. So the event E, we can write. So there are like two disjoint possibilities. One is uh, when uh, when Bob finishes before Claire. So x1 smaller than x2. This is one possibility. The other possibility is E intersection x1 greater than x2. This is when Claire finishes before Bob. Okay, so there are two disjoint cases possible. Um, right. So the probability. Okay. Let's write it down. So the probability of E equals probability of E um, intersection x1 less than x2 plus probability of E intersection x2 less than x1. Sure.
Yes, sir.
Yeah. So what is this? This is equal probability of E. So probability of A intersection B is equal to probability of A given B times B. So that's probability of E given x1 less than x2 times the probability x1 less than x2. Okay. Similarly, this is equal to probability of E given x2. Sorry, the probability of E given x2 less than x1 times the probability x2 less than x2. Okay. So what is E then explicitly? So how do you express E uh in terms of x1, x2, x3? So let's write it down. What is E in terms of sorry, what is probability of E in terms of x1, x2, x3? So this is equal to the probability. So let's write it down. So this is equal to probability of um, so this is the probability that uh, x1 is greater than x3 is greater than x1. Yeah, Alice is the last customer, right? So it's the probability that um, uh, yeah, it's so this is the probability that x3 is greater than x2. Just give me a second. Yeah, so it's a probability that x3 is greater than x2 um, given that x1 is smaller than x2, right? Yes, sir.
Yes, sir.
Okay. Um, okay, just give me a second. Let me just figure out one thing. Um, oh, okay. Sorry. X3 is for A. Oh, okay. I'm making a mistake over here. Sorry. So essentially x1, if x1 is smaller than x2, then um, it's not that x2 is less than x3. Actually, there's this correction to be made. Um, so this is equal to probability of of uh, of x2 being less than x1 plus x3, given that x1 is less than x2. So why is this equal to this? Because x1 is the first person to leave. X1 is the first person to leave. Then x3 comes and joins after x1. So x1 stands for Bob. So Bob leaves. Then Alice comes and joins after Bob. But if you just draw a figure, so let's say Bob takes time x1, and after that Alice takes time x3, but you want x2, which is the time that Claire takes, to be within this sum of x1 plus x3. So you want something like this.
Yes, sir.
Like Claire finishes before Alice finishes. So x3 is the time required to serve Alice, but Alice finishes at time uh, uh, x1 plus x3, right? So we want that x1 plus x3 is smaller than x2. Okay. Um, all right. Times the probability that x1 is less than x2. Okay. Now, okay, so let's just write it down. So times probability of x1 less than x2 plus here it's um, probability of x2 being smaller than x1 plus x3, given uh, x2 is smaller than x1. Oh, sorry, I've written the same thing. Sorry, it's probability of x1 smaller than
Smaller
x2
than
plus x.
X2 plus
Yeah,
X3.
exactly. It's just switch x1 and x2 in this thing. Probability of x2 less than x1. Okay. Now, uh, right. So I hope it's clear from a symmetry argument that that this thing is equal to this thing. It's clear, right? From an absolutely symmetry argument, because x1, x2, and x3 are IID random variables. The expression this summoned and this summoned are actually both the same. They are the
Yes,
same. They're equal
yes,
from a symmetry. Right. So we just need to compute one of them and do times 2. The next argument is uh,
Sir,
probability. Yeah.
sir,
Yes.
sir, I can't understand. Sorry to interrupt, sir, but I can't understand the step x2 is less than x1 plus x3, sir. Can you explain again, sir?
Oh, this step x2 less than x1 plus x3. Okay, so what is the
Yes.
problem? Are you aware of the problem? So the problem is this. So you have two customers, Bob and Claire, who are standing in a post office. Then Alice comes and joins. Alice comes to the post office, and whoever leaves. So Bob and Claire are currently being served by two clerks in the post office. So if Bob finishes first, then Alice goes and joins. Then Alice goes into the vacated clerk, and if Claire finishes first, then Alice goes into Claire's vacated clerk. And so the problem asks us, what is the probability that Alice is the last customer to be served? So basically, so let's say x1 is the time that the customer that essentially Bob took. X2 is the time, let's say, that Claire took, and x3 is the time that Alice takes. So x3 is the time for Alice, x2 for C, and x1 for B. So essentially, so let's draw a diagram. So what is happening over here? So here we have a condition. Condition is x1 is smaller than x2. So let's say Bob takes x1 time. So if Bob takes x1 time, then it finishes at x1 uh, on the line. Then Alice comes and joins after Bob. Alice takes x3 time. So this finishes at x1 plus x3, right? And Claire, so we want Alice to be the last person to Claire. So Claire should finish should finish sometime before x1 plus x3. So that's why we have x2 less than x1 plus x3. Is it clear?
Yes, sir. Yes, sir.
Okay. The other case is just the other case where Bob finishes after Claire. So we have x1 less than x2 plus x3. And by symmetry,
Sir,
both of these. Yeah.
I have one more doubt, sir. Why is exponentiation included in this question, sir? Why is it needed?
Exponential. Oh, the exponential distribution. Oh,
Yes, sir. Why
okay,
is
okay. Yeah, it's needed for you need memoryless property. So the memoryless property of the exponential distribution is what we'll use to solve this. Have you solved this problem?
no, sir?
Okay. I mean, there is a solution provided, but the solution is not rigorous. Okay, the solution is not rigorous. I'll explain why the solution. I'll bring up the solution later on. There is a solution given, but the solution is not rigorous. But anyway, so let's look at the problem first, and I'm going to give a rigorous solution. So let's see. Okay, so I hope this is clear now why we are getting this. So these two summons are same. So I'm just going to be bothered about computing this summon. Okay. So first is we have this term. We have probability of x1 less than x2. Okay. So what is this thing? So probability of x1 less than x2 is equal to probability of x2 less than x1. Because x1 and x2 are IID random variables. Both x1 and x2 are exponentially distributed and they're independent of each other. So they're IID random variables. So x1 less than x2 is equal to x2 less than x1. Okay. Now what is probability of x1 equals x2? Can you tell what is the probability of x1 equals x2? The probability of x1 equals x2 is equal to 0. Because x1 and x2 are continuous random variables. So what does this mean? So it means so probability of so now you have like three mutually exclusive events: x1 less than x2, x2 less than x1, x1 equals x2. So these three are mutually exclusive events. Um, this one's probability equals 0. So probability of x1 less than x2 is equal to half. So I'm just going to make a small statement. If sorry, lemma. If x and y are IID continuous random variables, then probability of x1 less than x2 equals probability of x2 less than x1 equals half. Okay, fine. So we know this part. We know that this is equal to half. So we are interested in computing this part. So probability of x2 less than x1 plus x3, given that x1 is smaller than x2. Yeah, so we are interested in computing this. Okay, so Right. So here is so this is where we need to do some computation. Okay. So x3 is a random variable. X3 is basically the time that uh, that Alice takes, right? Um, so you can write this as equal to uh, so essentially uh, we now have to uh, like you have to consider all possible values of x3. X3 can take all possible values from 0 to infinity. Um, so we need to consider like small finite elements and then integrate over that. So in particular, um, so yeah, so essentially this is equal to um, yeah. Okay, so how do you express this? Let's write this. So probability of x2 being this is probability of x2 being smaller than x1 plus uh, x1 plus x1 plus t, uh, given that x3 lies between t plus delta t and t x1 less than x2 times the probability of x3 lying between t plus delta t and t. We sum this over all t. Okay, so so if you take limits, you take limit delta t tending to 0. This is clear, right? How we get this from here, how we get this. So I'm going to now substitute x3. The x3 is a random variable. We need to substitute x3. So x3 can take values from 0 to infinity. So in particular, I can do a condition on this. So I can say x2 less than x1 plus t, where x3 is between t and t plus delta t times this and this. So this is equal to integral um, probability of x2 being smaller than x1 plus t uh, yes, uh, given that x1 less than x2, sorry, given that x1 less than x2 and x3 less than, sorry, greater than t and from t plus delta t. Uh, but notice that this side is independent of this condition because this has only x1, x2 and t. T is a constant over here. Okay. And so it's independent of this side. And so I'm going to erase this. This is independent of this conditioning. Okay. So we write this times the probability of x3 between t plus delta t. So probability of x3 between t plus delta t as delta t tends to 0. That is equal to the probability density function of x3. So x1, x2, and x3 are both exponential random variables. So their density function are same. So instead of explicitly substituting the density function, let's just call it as p, small p. Small p of t at dt. Okay. So this is the thing I need to compute. Probability of x2 less than x1 plus t, given that x1 is smaller than x2. Okay, So now this is what we are interested to compute. Probability of x2 being smaller than x1 plus t, given that x2 is greater than x1. Okay. Um,
Sir,
yes.
sir, one doubt, sir. What does IID stand for, sir?
What are the IIDs?
IID stands for, sir. What does IID stand for?
IID stands for independent and identically distributed. So
Okay.
they're identically distributed because both have exponential distribution, and they are independent because x1, x2, and x3 are the times required to serve Alice, Bob, and Claire, and they are assumed to be independent of each other. So that's why they are independent random variables and identical as well.
Okay.
So that's why they are IIDs. Okay. So we have to compute this term, right? Um, okay. So okay. So instead of computing this, let's compute the complement of this term. So let's compute what is the complement of this number. So complement is this, right? Probability of x2 greater than x1 plus t, given that x2 is greater than x1. This is the complement, right? So this is equal to probability of x2 greater than x1 plus t divided by the probability of x2 greater than x1. I hope it's clear why we get this, right? Okay. Now, so what is probability of x2 greater than x1? So probability of x2 greater than x1 is equal to half. We know this. This is equal to half. We need to compute this probability. So probability of x2 greater than x1 plus t is what we need to compute. Now x1 itself is a random variable. So this is equal to, so this is equal to integral probability of x2 greater than y plus t py dy, y from 0 to infinity. Okay. Um, so now we know what is probability of x2 greater than y plus t, because x2 is an exponential random variable and y and t are two constants over here. So this is equal to uh, 0 to infinity e to the power minus lambda times y plus t times lambda times e to the power minus lambda 1 v1. So lambda times e to the power minus lambda t comes out, and so we have integral e to the power minus 2 lambda y dy. Okay. And if you compute this comes out to be equal to e to the power minus lambda t upon 2. Okay. So then what does this equal? Okay, so what is this equal to now? So this is equal to e to the power minus lambda t upon 2 by half. So that is equal to e to the power minus lambda t, right? Okay. So what does this mean when we say that this uh, this conditional distribution is equal to e to the power lambda t? So this conditional distribution equals e to the power lambda t. Uh, it means that this conditional distribution also is an exponential distribution, right? Because what is the cumulative density? What is the CDF, the cumulative distribution function of the exponential random variable? It's also equal to e to the power minus lambda t, right? So essentially, what this means is that this random variable is also uh, is also uh, is also a exponential is also an exponentially distributed random variable, right? So now we are going to use it back in this formula. So what does this? What was this formula? So this is equal to. Um, so this is equal to integral. Let me just put a comma. Right. So plugging back into hash, uh, we have integral probability of mhm. Okay. Um, so your probability of uh, x2 less than x1 plus t, given that x2 greater than x1 times et dt. Now, you can explicitly plug in this value. Uh, So you have the value equals e power minus lambda t. You can explicitly plug this in over here, and pt is the exponential distribution. You can again plug that back and do the computation. Um, but you will see it's not required. Okay. Um, so in particular, you will notice that this this expression will come out to be equal to half. Okay, so why does it come out to be equal to half? Right. Um, okay. So what is uh, what is this expression? Um, okay. So to make this more rigorous, what we can do is we can define uh, um, so let's define a random variable w where probability of w less than t is equal to the probability of of x2 minus x1 less than t, given that x2 minus x1 is greater than 0. Essentially, it's the same thing I'm rewriting. Okay. Now, w and uh, yeah, okay. So we can write this as w. And from this expression, we get that w is also uh, exponentially distributed. Okay. So if it is exponentially distributed, you can write this as equal to in as a double integral of p some pz, let's say pz 0 to t dz times pt dt 0 to infinity. Okay. So essentially, what this comes out to be equal to, this is equal to probability of w smaller than x3. Okay. Now w and x3 are again IID random variables, and probability of w less than x3 is therefore equal to half. You can also explicitly get half by plugging in the value and doing the explicit integral, but this is a way to bypass that calculation. You can also do it in another way. Okay, so now we have computed this term, right? So we started off with computing this. So we have computed this to be equal to half. Probability of x2 less x2 less than x1 plus x3, given that x2 greater than x1. We have computed this to be equal to half. We know this is equal, yeah, so we have computed this term to be equal to half. And this is equal to half again. This is because they're IID random variables. So it's half times half, so it's 1/4. And this summand is by symmetry equal to this summand. So this is also equal to 1/4. And therefore you get the final answer is equal to half. So half is the final answer. Okay. Okay. Uh, are there any questions?
No, sir.
Okay then. Hello. If there are no more questions, then I'll stop the session.
Sir, where can I get the previous questions, sir? Previous session questions.
Sorry, I can't hear you.
Previous session questions, sir. This I couldn't attend 6 to 7 p.m., sir.
Oh, you can always go back to the YouTube lectures, right? So I'll give you the link to the YouTube videos. There is supposed to be, so there's a public sheet where I'm supposed to uh, um, where I'm supposed to upload it, but for some reason I'm not able to access the sheet. I do not have right access to that sheet, so I have to talk to NPTEL and ask them to give me the right access. But for now, what I can do is I can give you the link to the video in chat. So the previous tutorial session was uploaded to YouTube as is required to be.
Sir, could I get the link, sir?
Yeah,
Yes,
I
sir,
have
thank you.
given the link. Yeah, yeah. Yeah. All right. Yeah. Thank you for joining. I'm stopping the session.
Thank you, sir.
Thank you.